Continuing the discussion around attention score calculation, this is a Java implementation of the Python one that we saw in the last video. So in this case, we have a dummy tokenizer. It takes these two parameters, embedded dimension, which is the vector dimension. So 3 for all the 4 vectors, the positional, embedding, query key, and vector. For all those, the dimension will be 3, just like we saw in older videos. Vocab size I'm keeping 1000, although there is no model, but this is being used for generating the token IDs. So even in Python 1 where we simplified, it was the same case. So if you go to the tokenizer implementation, it is just taking these two and putting it in the instance variables, vocab size and embed dimension. And when it gets to tokenize a list of tokens, this is a string array list of tokens that it comes. So for each token, it calls this get token ID method that does a hashing. That hash number is put into the token IDs. Now this hash number will be uniform every time a particular token is passed to this. So this will always return the same number. So the implementation, we can see this is just a hash text it is doing, and using the vocab size. So there is nothing like random being used. So it will always give us same value for a same token. Now there are other methods like the get token embedding. This is for single token, and this is a wrapper over that for list of token IDs. So this is basically calculating that positional embedding initial vector. So given a token ID, it will create the embedded dim dimensional of vector. So it will return an array that contains um, n number of numbers, as where n is the embedded dimension. So in this case, we kept our embedded dimension 3 in the while creating the constructor. So that will be generating an array of length 3. That will be random int. The random int next int is being done with a seeded value of token ID. So every time this is called 3 times, it will always generate same 3 pair of random numbers. So that's the way it keeps this uniform when the same token ID is called twice. So if I'm passing the text this, that will generate a same token ID, and that will even generate the same positional embedding vector because of the seed value that was passed. Now coming back to the attention class, it's getting the token array, doing the token as we already saw, getting the token embedding that we just saw, the vector that it generates. And this vector is two-dimensional, you can see, because it will generate the positional embedding or token embedding for all the inputs. So token IDs is not just single string, it contains the token IDs of all these. And that's why this will return the token embedding of all those. So let's run this and see the output till this point. So see, this was the input text. These were the tokens. These were the token IDs that were generated, and this was the token embedding. Token embedding, since we have 1, 2, 3, 4, 5 tokens. So for each of the tokens, it generated a vector of size 3. So this is one vector. This is for the time. This is for the flies. This is for the like. This is for the and this is for the arrow. Just like in the Python example, for simplicity, in this case, we are making the query key and values same. So all these are same as these vectors. Now scores is being calculated. Let me go to its code first, then I will show. So here all these three, query key and value, are weighted with the token embeddings, and then this query key processor is doing perform the scaled dot product. This is again the same thing we saw in the Python. Starts at this point, it calculates the square root of the embedded dimension, so square root of 3 in this one, then does a cross product between query and the key transpose, just like we saw in that one, the Python example. So we are taking the query and doing the transpose of the key. Since query and key were originally in the same dimension, and we can see what was their dimension. So query was, number of rows were 5 by 3, and this is also 5 by 3. So 5 by 3 and 5 by 3 cannot be multiplied by the vector product, because the number of columns in the first matrix should match with the number of rows in the second matrix. In this case, 5 by 3, the number of columns in the first one is 3, and the number of rows in the second one is 5. So it cannot match. That's why doing a transpose makes it 5 by 3 and 3 by 5. So that's how the number of columns of the first matrix matches the number of rows of the second matrix by doing the transpose. And transpose actually lets it behave like a dot product. So this will get multiplied with exactly this. We'll see how this is being done. So see, these two are being multiplied. This was the query vector and this was the key vector transpose. So you can see this will get multiplied to these three the selection is not possible towards vertical line, but yeah, this 7.9, 1.8 and 0.52. 0, yeah, so these three and these three will get multiplied. This is same as doing the dot product of this with itself. So doing that, this table was generated. The scores after multiplying query and key transpose and dividing by square root of embedded dimension. So that is also done. It is divided by the square root of the embedded dimension, which is coming as this one, square root of 3. And you can see this multiplication generates an n by n table, where n is the number of tokens we had, the number of words you can call for simplicity in our original sentence. So this is for the time flies like an arrow. Similarly, this way. And this somehow shows a similarity between all those, but some operations are still pending, like the calculation of softmax. Softmax is also done the same way like in the Java one. So after doing the cross product, it is dividing all element by the square root of the value. Then it is doing a softmax implementation. We can see softmax, simple example you can consider is by doing a softmax, what we are doing is for making these each row, whatever the output it gave, the total sum we are trying to make as 1 for a particular row. And one way of doing is you just add all those and divide the values of the divide the added value to each of these elements. So when you add them up back, it becomes 1. But softmax provides a better approach, and the reasons I will just now show you. So see, in softmax, if one of the values is slightly larger, softmax makes it more dominant. For example, this array 2 comma 4, this one when done softmax returns these values 0.2 and 0.88. So 4 was slightly more than 2, and it enlarged its effect in the list. In comparison, the sum normalization does this. 2 becomes 0.33 and 4 becomes 0.66. So this is better, helps in clarification when you want higher confidence in prediction. Similarly, for dealing with negative numbers, the sum example can return a 0 when position negative numbers are there. The total sum can become 0, so division by 0 becomes minus infinity to infinity. So that is a issue. In this case, we do exponential for softmax, so that makes it positive, because x is negative, but e to the power x will always become positive. Hence, this is also, in this term also, this is better. So coming back to our code, let's see the further things.